Let's take a look at the electron configuration for the carbon atom. That is going to be 1s2, 2s2, 2p2, which is solely based on its position in the periodic table. We don't really care about the core electrons, which are the 1s electrons, so I don't care about those. What I do care is my valence electrons over here. So these are my valence electrons. And if I were to depict those visually, what I'm going to get is a carbon atom. Then let's say I have some sort of energy scale, and I've got my 2s electrons over here, and I have 3 levels for 2p electrons like that. We're going to put 2 electrons onto the s level and 2 more electrons to the p level. The valence bond theory suggests that to make a covalent bond, each element needs to supply an electron. So for carbon to make 4 bonds that we would normally expect to see for this element, we need to decouple the s electrons and promote one of them onto the p orbital. So basically we are going to take one of those electrons and move it over here. What that would give me is an s orbital and then my 3 p orbitals with 1 electron each. So I have 1, 2, 3, and 4 electrons over here like that. This way we'll end up with 4 singly occupied orbitals ready for bonding. The valence bond theory refers to that as an excited state atom, whatever that means. Well, so far so good, right? Now, let's take a quick detour here and go back to Gen Chem for a hot moment and review the shapes of our atomic orbitals. So if I have an s orbital, we would normally expect a sphere like that. So this is my s orbital. If I have a p orbital, however, we have 3 of those, so we're going to have one in the form of the infinity sign along one axis, another one along the other axis, and then the third one along the third axis, like that. So if I combine it all together, it'll end up with an atom with a spherical s orbital surrounded by the 3-dimensional flower of the p orbitals around it. And my question here is going to be, so how exactly am I going to use this monstrosity to construct a molecule? If, for instance, I wanted to build, I don't know, a CH4 molecule, for instance. Here I have CH4, methane. Do I just hang my hydrogens on the p orbitals? And what am I going to do with the s orbital? That makes very little sense. On top of that, we know from the experimental data that CH4 methane molecule has a tetrahedral shape with the HCH bond angle being roughly 109 degrees. So if I were to draw it, I would show my carbon, then one hydrogen, second hydrogen, then third hydrogen kind of looking towards me, and then the last hydrogen looking away from me over there. And the bond angle over here is going to be roughly 109.5 degrees. It's about 109 degrees and 28 minutes, something like that to be precise. What is important here, though, that it doesn't really fit our model with 90-degree angles between p orbitals. So what's up with that? After pondering at this problem for a while, Linus Pauling, an American chemist, introduced the concept of hybridization in the mid-30s. His work in the field of chemical bonding resulted in him earning his first Nobel Prize in 1954 for his research into the nature of the chemical bond and its application in elucidation of the structure of complex substances. But I digress. Back to hybridization. So the hybridization is the mathematical model that describes a partial overlap of the orbitals. To simplify that even further, we are going to say that the orbitals mix together, forming a set of hybrids, which then participate in bonding at appropriate angles. So if I have one s orbital and I mix that s orbital with 3 p orbitals, what I'm going to end up with as a result is going to be 4 sp3 orbitals, and those orbitals, each of those is roughly 25% in the s character and about 75% in the p character. If I leave one of my p orbitals as is and now mix an s orbital with 2 p orbitals like that, what I'm going to get is the p orbital is still going to be hanging on its own, but then I'm also going to get 3 sp 2 orbitals. Now each of those hybrids is going to be roughly 33% in the s character and about 66% in the p character. Lastly, if I'm going to keep my 2p orbitals as is and only mix one s orbital and one p orbital, then what I'm going to get in this case is 2 p orbitals, and I will also have 2 s p orbitals, and each of those is now about 50% in the s character and about 50% in the p character as well. And exact percentages will depend on the exact molecules, so it's fine to average those out for our purposes. Now, couple of important things that I want to point out here. The first thing is that the number of orbitals is always going to be the same. We have 4 orbitals in, and we are going to end up with 4 orbitals coming out of our hybridization. This is a very important principle that we are later going to see in the molecular orbital theory when we start talking about that the atomic orbitals, because technically the s and p orbitals, those are atomic orbitals. Once they go through the process of hybridization and once we form new quote-unquote hybrids, those would be considered molecular orbitals because we are using them to make molecular bonds. And the main principle of the molecular orbital theory is that the number of atomic orbitals, I will even write it out, the number of atomic orbitals has to equal to the number of the molecular orbitals. So anything that comes in is going to come out in the same quantity. So if I have 4 orbitals to begin with, I am going to end up with 4 orbitals at the end of it. While you may also recall some other fancy hybridizations from general chemistry, we'll limit ourselves just to what is possible for the second period elements here, where basically our core elements of the organic chemistry live. And not to mention that the whole concept of hybridization and predictive power of the VSEPR theory kinda goes out of window the lower in the periodic table we are. Now, the reason why I'm mentioning the VSEPR theory in conjunction with the hybridization all the time today is because they are intimately intertwined and one flows from the other one. Let me explain. So let's take the SP3 hybridization as a starting point for our discussion here. Mixing of 1s and 3p orbitals gives us 4 SP3 orbitals. I will remind that here as s plus 3p gives me 4 sp3 orbitals like that. And each of those sp3 hybrids are going to have both characteristics of s and p orbitals, and all are being equal in energy. In other words, they're going to be degenerate. So from the perspective of the Valence Bond Theory and from the perspective of the shapes of those orbitals, we know that the s orbital is a sphere again, and the p orbital is this infinity sign or figure 8. Once I mix those together, I'm going to end up with 4 sp3 orbitals, where I have one large lobe and one little tail, so it kind of looks like an s orbital, a very long s orbital, with a little bit of a tail on the side from the p orbital. And since they are all equal in energy, these orbitals will also arrange themselves around the central atom in the most symmetrical way possible due to the electron repulsion. So if I have a central atom over here, doesn't matter what sort of atom that is, maybe carbon, maybe something else, I'm going to have one orbital over here. I will have the next orbital like that. Then I'm going to have my third orbital looking at me, and I will have the last orbital down there looking away from us. So in other words, it's going to look like if, let's say, this is carbon, I have one bond here in plane of paper, the second bond here in plane of paper, then the third bond is going to be at an angle looking at us, and the last bond is going to be also at an angle, but now looking away from us like that. This, as we know from the VSEPR theory, is a tetrahedral shape. And when it comes to the tetrahedral shape, the bond angle that we have over here is about 109 degrees, 109.5 degrees to be more precise. That means that for our core elements of organic chemistry, such as carbon, nitrogen, and oxygen, we're going to have the following molecular shapes. It's going to be tetrahedral for carbon with a bond angle of about 109 degrees. It's going to be trigonal pyramidal for nitrogen with the angle of roughly 107 degrees, and it's pyramidal rather than tetrahedral in this case because nitrogen has an electron pair over here, and when it comes to the electron pairs, those guys are invisible. So this way for oxygen we are going to have the band shape with a bond angle of roughly 105 degrees. For the exam purposes, typically it's going to be perfectly fine if you just say that all of those types of species have a bond angle of 109 degrees of 109.5, because for exam purposes and within the scope of our course, we don't need to go into the minute details of the bond angles, and besides, in most cases, there is no way of knowing the exact angle unless you do the specific experiment to measure that or do quantum chemical calculations, which we obviously don't do here. If we now move to the SP2 hybridized species, we're going to have the following picture. Now I'm going to have one of my p orbital not participating in the hybridization, so it's going to be a free p orbital. So as a result, I'm going to get a free p orbital, and I'm also going to have 3 SP2 hybrids. Those orbitals arrange themselves around the molecule in the following fashion, where my hybrids are going to make a trigonal planar shape, and the p orbital is going to be sitting above and below that, like this. So in other words, this is going to look something like this. I have a carbon atom, I have one bond, second bond looking towards me, third bond looking away from me, and I have my p orbital over here like that. That comes very handy when we have double bonds, so that the p orbitals, when they overlap, they can make a pi bond, which is going to look somewhat like that, where the p orbitals overlap above and below the plane of my molecule, forming a bond in between the carbons in addition to the sigma bond that I have in the middle of those. Geometry for this configuration is going to be trigonal planar or band, depending on whether we have our electron pairs or not. So if, let's say, I have a carbon with a double bond and a couple of other bonds, that is going to be my regular trigonal planar geometry with the bond angle of roughly 120 degrees. And if I have, let's say, nitrogen, where I can have a double bond on one side, single bond on the other side, and an electron pair, which I will show like this for right now, since we do not see the electron pair, that one is going to represent a band shape. Finally, if we move to the SP hybridized species, we'll get a mix of 2 unhybridized p orbitals that I have here circled in green, and 2 hybrids that are going to be my SP orbitals. These species will arrange themselves in the linear fashion around the nucleus, giving me a picture like that, where my p orbitals are going to be above and below in one plane, and then again above and below, or rather I should say in front and in the back in the other plane. So those two are the p orbitals. In other words, that going to look like, let's say if I have a carbon atom, I'm going to have one p orbital over here and another unhybridized p orbital down there. This type of bonding becomes very useful in the case if I want to make a triple bond, because then my p orbitals in different planes can interact with each other, and that going to end up giving me a carbon-carbon triple bond, or carbon-nitrogen triple bond, or nitrogen-nitrogen triple bond, doesn't matter. And the bond angle in this case is going to be 180 degrees, and the geometry here is going to be linear. So whenever we are dealing with the molecular geometries, the easiest way is to always go from the hybridization to the VSEPR theory domains, from there to the shape based on what we are seeing here. And whenever we are dealing with hybridizations, thinking about all the orbitals, their spatial orientation and such is kind of difficult and tedious to some extent. So there is a very easy hybridization trick. You just count the number of things around your atom of interest, and if you have 4 things, that's going to be sp3 hybridized species, 3 things sp2 hybridized species, and 2 things are going to be sp hybridized things. And by things here, I mean electron pairs or other atoms. So let me demonstrate that with a simple example. So let's say I have carbon with 4 bonds around that. Well, that carbon has 1, 2, 3, 4 things around that, which means that that one is going to be an sp3 hybridized species. Or let's say I have nitrogen with 3 bonds and electron pair. When it comes to the things, I'm going to count 1, 2, 3, 4, because an electron pair is a thing, so to speak. So again, I have 4 things around my nitrogen, which is going to give me an sp3 hybridized species. Or let's say I have a situation where I have a double bonded carbon like that. Well, in this case, I have 1, 2, 3 things around my carbon, which means that that is going to be an sp2 hybridized species. Let's actually look at some real examples. In my first molecule, let's look at oxygen over here. So oxygen has 1, 2, 3, 4 things around that, which means that oxygen is sp3 hybridized. Now, for the next molecule, I'm going to focus my attention on this carbon. Again, this carbon has 1, 2, 3 things around that, which means that this carbon is sp2 hybridized. The next molecule, I am again going to focus my attention on carbon. This carbon has 1, 2, 3, 4 things around that, so that is going to be an sp3 hybridized species. In my second row, I will first look at the carbon. That carbon has 1, 2 other groups around it, which means that this carbon is sp hybridized. In the next molecule, if I look at my nitrogen, then I will see that nitrogen is connected to carbon and it has an electron pair, which means that nitrogen is connected to 2 things, so that is also an sp hybridized species. And in my last molecule, I'm going to look at the nitrogen as well, and in this case, nitrogen is connected to carbon, oxygen, and we have an electron pair. So that one is connected to 3 things, which means that the nitrogen is sp2 hybridized. Now, the bond line structures, those guys can be quite tricky. Always remember the implicit electron pairs and hydrogens. So let's say I will look at this carbon over here. If I asked you what hybridization do I have for this one, and if you told me sp, I would give you a very stern look, because we have a couple of hydrogens attached to that carbon, which means that that carbon is attached to 4 things, so that is going to be an sp3 hybridized species. Next, let's look at, let's say, this oxygen over here. Well, for this oxygen, again, if I pay very close attention to how my structure is drawn, I am missing the implicit electron pairs on this oxygen, which means that this oxygen is connected to 4 different things, which means that that is an sp3 hybridized species as well. Next, let's say I'm going to look at this carbon over here. Well, it looks like that carbon is only attached to 1 thing, but I remember that on top of that we have 3 more hydrogens there that are implicit hydrogens, which means that this carbon is as well an sp3 hybridized species. Now, for a change, let's look at a carbon, let's say over here, all the way on the other side of my molecule. Now, this carbon is connected to only 1, 2, 3 things, if I keep attention to the structure and I remember my implicit hydrogen, which means that that carbon is sp2 hybridized. Easy enough? Well, that's gonna be it for this tutorial. Remember to check the organicchemistrytutor.com for more practice questions, tutorials, and notes. Drop your questions and comments below, and I'll see you in the next one.